Weirs are instruments for determining flow rate in liquids by measuring the height of the water relative to an obstruction, in this case the weir, in an open channel. The first weir we're going to talk about is a rectangular, sharp-crested weir. Here's our rectangular, sharp-crested weir. So I've got my little pointy black thing here. This is the actual weir, and it has a height of P. The water height over the weir we represent with the letter H. And the depth of the weir into the page is L. I can use the energy equation and reduce it. To terms of my weir, which will be pressure 1 over gamma plus the height where little h here is any height above the weir. And we're going to see that P is equal to 0 because it's an open channel. My h's cancel. So my velocity over the weir is 2gh, and we're going to take the square root of that. Our flow rate is equal to velocity times area, so we can integrate that from 0 to h of velocity square root of 2gh times length, and then that changing height h. And we'll end up with an ideal flow rate, Q, is equal to 2/3 the length times the square root of 2g times height to the 3/2. Now, of course, our weirs do not work in ideal situations. We've got actual flow with viscous effects, and we need to add a discharge coefficient. So our actual weir equation for a broad crested weir is Q is equal to 2/3 our discharge coefficient C subscript D times the square root of 2g times length into the page, so the width of the weir, times the height of the water above the weir to the 3/2. Let's say we're given water flowing in a rectangular channel that has a depth of 1 foot, and it's flowing at a velocity of 3 feet per second. Find the required height of the sharp-crested weir to raise the upstream water level to 4 feet. Use a discharge coefficient of 0.62. So we're going to start with our flow equation for a broad-crested weir, which is 2/3 CD times the square root of 2g, length times height to the 3/2. I've been given CD, and I know that gravity is 32.2 feet per second squared, but that's all that I know. So we're going to have to use some continuity, where flow in is equal to flow out, meaning our velocity times our area should be consistent throughout the entire system. We were given our velocity at 3 feet per second, and our area is going to equal the depth of 1 foot times the length that we were not given. So that means my flow rate is 3L. So I can now plug that back into my equation. 3L is equal to 2/3 0.62 times the square root of 2 times gravity times length, and then the height above the weirs, which we're looking for, 3/2. My lengths are going to divide out, and my height solves to be 0.935 feet. So this is the height of the water above the weir, and I want the height of the weir. So that's going to be P, which is 4 feet minus 0.935. So our height of the weir, P, is equal to 3.07 feet. What if the rectangular sharp-crested weir did not extend the entire width of the channel? Say, for example, this suppressed rectangular weir, where L is still the width of the entire channel, but we've got the smaller area, B, that our water is flowing through. The discharge coefficient's going to change. We're going to use the same equation. Q is 2/3 CD square root of 2G H to the 3/2, but instead of the full length L, we'll use the weir width B. Now we have to be very careful and do some experimentation if our weir gets too constricted, because we are going to have contracting on the sides, so it's going to come in here a little bit before it comes on out here, and that's going to change our flow rate a little bit. The most accurate weirs that we can use to measure flow are triangular weirs. So we've got here the V-notch weir. Now the triangle itself has an angle of theta, and this water depth here is our H value. So our flow equation turns into 8/15 of CD times the square root of 2G times the tangent of theta over 2 H to the 5/2. A little bit more complicated, but we've got a little bit more complicated shape. This time we're given a flow rate over a 45-degree triangular weir of 0.023 meters per second. Use a discharge coefficient of 0.6. Find the head or the depth of flow in that triangular weir. Again, using our flow equation, but this time for a triangular weir, we'll plug in all of our known values. And solving for H, we get a value of 0.274 meters. Both the triangle weir and the sharp-crested weir are very thin weirs, where it's just changing that flow. Another option is a broad-crested weir. So we see here a much fatter, longer rectangular weir to slow down that water. And what we're looking for here is to reach critical depth over this broad-crested weir. So we're going to maintain our energy over the weir, and remember the energy grade line is V squared over 2G away from the hydraulic grade line, which is going to be the water surface depth. We still have H, which is height above the weir. We're still going to have P, which is the height of the weir itself. And that's going to give us a flow rate equation of CD times the length into the page, so that's the width of the channel, the width of the weir, times the square root of G, times 2/3 of H raised to the 3/2 power. So given this broad-crested weir, we have an upstream depth of 1.6 meters. We have a broad-crested weir that is 1 meter high above the bed of the open channel. The width of the channel into the page is 5 meters, and we're using a discharge coefficient of 0.51. Find the flow rate and the critical depth. Flow rate is going to be coefficient length square root of g times 2/3 h to the 3/2. Plugging in what we know, Q is going to equal to 0.51 times 5 meters, 9.81 meters per second squared, times 2/3, and h is the height above the weir, so that's going to be 1.6 minus 1 meters to the 3/2. And solving this, we get a flow rate of 2.02 meters cubed per second. Now remember, way back with rapidly varied flow, we could find the critical depth using the area of the critical depth over the width and setting that equal to flow rate squared over gravity. So my critical area is going to be 5 meters times that critical depth cubed all over 5 meters. Set that equal to my new flow rate. And gravity. And I find that I have a critical depth of 0.255 meters.